for you. You have a bell ringer question in Google Classroom, and it's the one about centripetal acceleration. So that's the one as soon as my marker decides to work. So it's this one right here is in Google Classroom. So please answer that and pause the video and we'll go over the question here in a minute. Alright, so what is centripetal acceleration? What are the forces that can cause a centripetal acceleration? So essentially, centripetal acceleration is acceleration in a circle. Okay, so that would be anything that travels in a circular path. Okay, so the acceleration is actually towards the center of the circle, and then the velocity, whatever path it's following, is tangential to the circle. Okay, so you guys should know what a tangent line is. So a tangent line to that circle is just something that touches it at one point. So the acceleration is towards the center, and the velocity is kind of away from that circle. So centripetal actually means center seeking. Okay, so we're going to kind of reinforce what you read about with the centripetal acceleration and rotational motion. Okay, and then there is a lab that goes with this, but we'll be doing that another day. Okay, so what are the forces that can cause a centripetal acceleration? Well, that would be gravity. If you read about this, if you looked it up on the internet, that would be like satellites. We can have tension. Okay, that would be anything on a string or a chain or a cable, stuff like that. And we can also have friction. Friction can cause a centripetal acceleration. That would be like a car turning, okay, or you running around an embankment on a curve or something like that. Okay, so we're going to talk a little bit more about circular motion here, and you can fix things that you did if you had a worksheet that was due. There will be a worksheet at the end of this lesson involving circular motion problems. Okay, so I have a video that I would normally play with this. I'm just going to provide you the link in Google Classroom for that. But we're going to look at centripetal acceleration, the forces that cause it, how those forces work in the system, and you're going to be able to explain the difference between projectile motion and circular motion. Okay? So, starting out, I kind of talked about this already. So uniform circular motion, it's just an object is moving in a circle. It's got a fixed radius, okay, and constant speed. So that constant speed is the uniform part of that. Okay, and then again, I said the velocity vector is always tangent to the circle. Just so you guys are going to have the notes in front of you as well, so that way you don't have to kind of follow 100% as fast as I go in the video. It's going to be a little bit quicker because you may have read about this already, so we're going to try to get to the problems at the end. Okay, question down here at the bottom is how can we determine the change in velocity, or delta V? Okay, so think about that for a minute. How could I find the change in that vector to that vector? Those are my tangent vectors, my tangential vectors that represent my velocity for my centripetal acceleration. If you said, well, change is difference, so we can just subtract the vectors. So it'd be V1 minus V2. And what you could do if you wanted to, if you had an angle or something like that, you could find your components and subtract the component to see what your resulting vector is. Okay, or tip to tail. Tail would kind of look like this. So if we do vector 1, kind of off like that, and then vector 2. So if we're subtracting, you have to flip the vectors around. So that one would be going kind of back that way. So then your change in velocity would be whatever that vector is. Okay, so this would be resultant vector. That's going to be what your change in velocity would be, because you're going to subtract those two vectors. Okay. So for the centripetal acceleration, I kind of told you this a little bit already. Centripetal acceleration is a center-seeking motion. So it always has acceleration towards the center of the circle. So its magnitude is equal to the square of the speed divided by the radius of the motion. So I have an equation down here for you for centripetal acceleration. So this is probably a big thing, and then to here also. Okay, and then we'll write down the equation. So centripetal acceleration, you may have written this equation down already during your reading. So A sub c, that little c stands for my centripetal acceleration. That equals v squared over r. All right? So that's velocity squared over radius of the circle that it's traveling around. So that radius could be like a radius of a turn. It could be a radius of a rope or a string. If we're trying to say gravity, then it could be like the radius of from the satellite to the center of the Earth, something like that. Okay? So then a period, for you people that had trig, you already know what that is. Okay, so that's like how long something takes to make one cycle. Okay, so we can describe our period here as, we'd have to solve for t here to actually get the period, but we can describe the circular motion by its period using the time it takes for one revolution. So the t is your period, and it's always going to be given you in seconds. So how long does that take to go one time around the circle? Okay, so one revolution of a circle is equal to the circumference of a circle. It's 2 pi r. Okay, so we can find our velocity with this formula down here. Okay, because circumference of the circle is 2 pi r. So if we're spinning something in a circle, right, so we have whatever, a string, we're spinning something in a circle, well, the circumference is the distance that I traveled, right? And then t is how long it took me to travel that distance one time. So 2 pi r over that time is going to give me my velocity. Okay, so if you see what we're going to do next, since I have a velocity down here, and that's used in the equation up here, we can substitute that 2 pi r over t in for v squared. So I have some steps here below, not really necessary to know all the steps, but just to show you how we get our big and final centripetal acceleration equation. Okay, so this is substituting in that v, okay, which is 2 pi r over t. So we're putting it into our equation there like that. So we have to square it, and when you square it, it becomes this. So that is our big centripetal acceleration equation. Okay, so we can use that to figure out how fast something is spinning around in a circle. We can use that to figure out how long it takes to go one time around the circle. We could use that to figure out a radius, depending on what we're looking for. So there's your big equation for this module, this lesson, excuse me. Okay, so this page has them all. So if you need to go back to them, go back to your notes in Google Classroom, and you'll have all the equations there. Okay? So with acceleration, Newton's second law, we have a centripetal force. Okay? When an object moves in a circle, net force towards the center of the circle is called centripetal force. And again, that can be caused by tension, friction, gravity, and there may be others. I have to look at it because we could have magnetic force could probably cause centripetal acceleration. Nuclear, I don't know about that. Electrical could probably cause something like that. Okay. And it says, give a scenario for each agent of centripetal force. I already did that earlier in the video. So tension would be a rope or a chain. Friction would be driving around a bank or a curve. And gravity would be like a satellite. Okay. So if we're talking force, so we know, and this is kind of written backwards. Let's write it like this. So force equals mass times acceleration. If we're talking centripetal acceleration, So really, if I want to go from that acceleration to a force, the only thing that we have to include in there is a mass. Okay? So you can include that in another equation, so that would be net force. And when we do our lab for this section, we're going to be calculating centripetal force. Okay? So that's just bringing Newton's second law into here. Okay, so here is one of your quote-unquote agents. Okay, so the car is turning. So as the car turns, passenger feels a fictitious outward force called the centrifugal force. Okay, so if you wanted to look into this more, it's in the video that I supplied in the links. However, if you're just kind of thinking this car turns that way, right? If you're in the car, then your body is going to want to kind of keep going that way. You're going to like slam up against the side of the car depending on the speed of the car, right? So some people have said that that is a centrifugal force, which is not really the case. Okay, the thing that's keeping us moving that direction, the thing that gets you to kind of hit the car door, that's actually your inertia, because your body wants to keep going that way, right? So your body wants to fight against that centripetal acceleration or that centripetal force. Okay, so you could see some questions about centrifugal force, but it's not actually a real force, and it is just kind of it's inertia making the tendency of your body to go out towards the car. Okay, so same kind of thing. If you were on one of those big swing rides, okay, you're swinging out, the thing starts to speed up and you feel the force pushing you out, right? That's not the centrifugal force, that's just your inertia. Your body wants to stay where it is, but the thing's speeding up. Okay? So if we're thinking about using Newton's laws of motion, so if the only difference is that we have a force here. So rather than centripetal acceleration, it's a centripetal force, right? So you're going to feel that car is turning, and then we have our centripetal force towards the middle there. That's going to be kind of what you feel on your body. So your body's going to be trying to resist that centripetal force due to the inertia outwards. All right, so why are some curves on highways banked? Number one reason, because they have to turn to get to a certain city. But actually the bank is what I'm talking about, is how it's kind of on an angle like that. Okay, so it's kind of banked like that rather than just a flat curve. So if you think about the curves on Highway 34 going to Lincoln, the embankments are actually angled a little bit, and the reason that we do that is because we can use friction as our friend here. So friction will cause that car to stay on the bank there, okay? So here's an explanation for you. So roadway produces a horizontal component, the normal force component in the same direction as the desired centripetal acceleration, and so it contributes to accelerating the car and make it round the curve, so you don't fly off the embankment. Okay, and then here's another thing. I think we had a video about this stuff a while back. G-forces. So pilots feeling G-forces. So think about the video that we had, the two guys spinning around in a circle. Okay, so let's try a centripetal force or centripetal acceleration problem here. So we have a 13-gram rubber stopper. Let's make that a little bit bigger. Okay, so you got a 13-gram rubber stopper spinning around, attached to a 0.93 meter string. Stopper is swung in a horizontal circle, making one revolution in 1.18 seconds. Find the magnitude of the tension force exerted by the string on the stopper. So tension is equal to centripetal force. Okay, so force of tension is our centripetal force. Oops. So don't be confused by the fact that it says find tension. We're just looking for centripetal force. Okay, so let's plug stuff in. So let's write out our equation. So it's m 4 pi squared times r all over t squared. And we actually have everything we need, except you got to think about that right there. I think that's the only one we got to worry about. It's 13 grams. If we're working in forces, then we got to have newtons and meters. So we have our mass. It's actually, so we're going to move 0.013 kilograms. Our radius, that's just however long the string is, so 0.93 meters. And our period, it tells us that it takes 1.18 seconds per revolution. Got enough stuff, just plug it in. Okay, so 0.013 kilograms times 4 pi squared times r, all over 1.18. I forgot my labels on my 0.93, that's fine. Okay, so let's put all that in our calculator. So you can just kind of go from left to right. I would do the whole top first, like do this, and then press enter, and then divide it by the bottom. That'd probably be the best way to make sure you didn't make a mistake in the calculator. So 0.013 times 4 times pi squared, the square button is 2 down from pi, times 0.093, and then I'm going to press enter and divide that by 1.18 squared. And I get 0.034. Okay? So that is the magnitude of the tension force. And I'm going to double check my numbers here because that seems kind of small. But it's only a 13-gram rubber stopper. So let's double check our numbers. 0.013 times 4 times pi squared times 0.093. Oops, it's just 0.93. Maybe I put an extra 0 in there. Divided by 1.18 squared. And I get 0.34. I think I had an extra 0 in there. Okay, and that is in newtons. Okay, so make sure you double check your work. I accidentally had a 0 in here when I put it in my calculator, so I had to fix that. So that is a centripetal force problem with the rubber stopper, and this is going to be kind of what we're doing when we do our lab, so it'll be kind of fun. All right, let's check out another one. So give this one a shot before I do it, so please pause the video for a few minutes, see if you can get it, and then press play, and we'll go through the answer. All right, so I have an extra thing on here. Draw a motion diagram and a free body diagram. So if you wanted to, I'd say we got our dude with the fishing pole here, and this is the motion of the weight. Okay, so that's 0.75 meters. Excuse me. Yeah, well, it doesn't matter that much. Let's say you're spinning it that way. Okay, so then we need to do a free body diagram. So these are kind of different. So the free body diagram, we actually have gravity going down, and then we have our centripetal force going towards the center. Okay, and then really that is, so that centripetal force, and I guess we could say the tension rather than centripetal force because it's a fishing lure on a string. That tension is what's going to keep that, it's kind of goofy, but it balances out gravity because it kind of keeps that spinning where it is. All right, so you can see he's going to have to spin it a little bit faster to make sure it doesn't fall, but centripetal force is actually going to keep that thing spinning where it is. All right, so that would be, and this is towards the center. It's kind of goofy if I had like a three-dimensional arrow here, that's like towards the center. All right, so that would be like following this path. If you can kind of picture that. I'm not going to have you draw free body diagrams with centripetal force or acceleration very often. Okay, so let's plug stuff in. So force of tension is equal to my force of, or my centripetal force. So that's going to be mass times 4 pi squared r over t squared. Plug everything in. It's actually in kilograms for you right now also. So you're welcome. 4 pi times radius. So our radius is 0.75 meters, and that's over a period of 1.2 seconds. And that's a squared, and then I need a square with my pi. Okay, let's plug it in, let's see what we get. So 0.028 times 4 times pi squared times 0.75, doing all that on the top, divided by 1.2 squared. I got 0.5757, so let's say 0.58. So my centripetal force is 0.58 newtons. So that is pretty much, that's the centripetal force, that is tension. Okay? So hopefully those aren't too bad. You could be given a centripetal force, and then you have to find like a period or find a radius or something like that. Okay? So this one right here is kind of an interesting problem. There's a problem on the worksheet that you're going to get. It uses airplanes rather than this idea. Okay, but we have kind of a loop here. And then you got a clown on its car here. It's a little clown car. Give him some curly hair and a nose. Alright, so he's going into his loop like that. So Carnival Clown rides a motorcycle rather than the car. My bad, so we're just going to go with the car for now. Down a ramp along a large vertical loop. The loop has a radius of 18 meters. Okay, so that's our radius. What is the slowest the rider can have at the top of the loop so the motorcycle stays in contact with the track and avoids falling? Okay, a hint, at the slowest speed, the track exerts no force on the motorcycle at the top of the loop. Okay, so let's think about our car or motorcycle, whatever you did, okay, at the top of the loop. Okay, so let's think about the forces at the top of the loop. All right? So it says here, at the slowest speed, the track exerts no force on the motorcycle at the top of the loop. Well, what are the forces here then? Track's not exerting any force. Well, normally the track would be exerting a force, so that would be called the normal force, right? But there is no normal force. So what's the force up here? Well, the only thing that's exerting a force up there, gravity. So at the top of the loop, I have gravity pulling me down. But where is gravity going? Gravity is going towards the center of the circle. So at the top of the circle, my gravitational force, okay, gravity, is equal to the centripetal force. All right, well that's interesting. We could set these two equations equal to each other. So we have mass times the acceleration, that's gravity, if we want that. And my centripetal force, that's mass times 4 pi squared. Let's just leave that out for now. Times radius over period. Okay, so you can see that that mass will cancel out when I set those two equal to each other. So let's put the numbers in here. So 9.8 meters per second squared, that's my acceleration due to gravity. Didn't need that. And then we have 4 pi squared. My radius is 18 meters. And I don't know my period. I don't know how long it takes for the clown to go around the loop once. Okay, so we have to do a little bit of algebra here. Multiply the t out of the bottom to get it over to here. Okay, and then we're going to have to divide by 9.8 meters per second squared to get it over here. So then we can plug this stuff into our calculator and get what t is. So 4 pi squared times 18 divided by 9.8 meters per second squared. And that gives us a period, and I forgot to do period squared. So period squared is 72.51, and that's going to end up giving us a second squared if we follow the labels. And then t, so let's square root that, and we will get 8.52 seconds. So that's how long it takes the clown to go around the loop-de-loop once. Okay, so then we could take that, put it in our velocity equation. Okay, so velocity is going to be the distance around the circle, so 2 pi r, over that period. All right, so we have that information. Let's plug it in. So 2 pi times 18 meters over 8.52 seconds. Let's put that on our calculator, see what we get. So 2 pi times 18 divided by 8.52, and we get 13.3. And that'll be meters per second. So that clown's got to drive his motorcycle or his car 13.3 meters per second if he does not want to come crashing down at the top of that loop. So kind of cool. You can figure that stuff out with some centripetal acceleration. Okay, so that's what some of the problems are going to look like. This one's kind of the harder problem. And I will skip forward to these. I'll skip that. You can come back and watch that if you wanted to. It's a hammer throw. It's pretty cool. And looking at this worksheet. Okay, so please pass the worksheet out. You pause the video and then restart the video. It'll take a couple seconds to look at a couple of these and give some hints and possibly work through one. All right, so number one, can you go around a curve with the following acceleration? So a zero acceleration vector. Can you go around or go in a circle with a zero acceleration vector? You got to explain. The answer is no, because acceleration is a change in direction. So as you're going in a circular path, you're always changing direction. Okay? Can you have a constant acceleration vector? That is yes, that would be centripetal acceleration. Okay? So we got a yo-yo. So kind of answer the questions on the yo-yo. C, if you let go of the string on the yo-yo, which direction would the toy travel? So that would be, remember, a tangential path to the circle. Okay, so you'd have to use Newton's laws of kind of explaining that. Number 3, you can just use your equation. And then number 4, you're going to be working through A, B, C, D, and then rank them according to their centripetal accelerations from least to greatest. Okay. And we have a hammer throw one, so just like that video, 7 kilogram hammer, 1.8 meters from the axis of rotation. Okay, so centripetal acceleration, what's the tension on the chain? So that one should be pretty easy, just find the centripetal force there. Okay, rotating rod, 15.3 centimeters long, axis through the end of one rod. Rod has a constant speed of 2,010 meters per second. Okay, so for this one, we're going to have to convert this to meters. Okay, so if we're trying to find centripetal acceleration, we need 4 pi squared r over t. Okay, well, we don't have t, so then that means we're going to have to go to this equation, 2 pi r over t, because we're going to have to find or use that velocity and the radius to find t. Okay, so then that gives you enough information to go through that one. Okay, then the second question, if you were to attach a 1.0 gram or 0.001 kilogram object to the end of the rod, what force would be needed to hold it on the rod? So with that one, you're just looking for centripetal force for that one. Okay, so we have that introduced, so that way we can use centripetal force. Okay, that's your mass. So you're just finding centripetal force. Okay, and then this one is just like the clown problem that I went through. So you have to work through it about the same way. We are given a mass here. All right, so that way you can use that. So it says, what's the radius of the plane's loop? We're kind of working backwards from where we were before. Still at the top, you're going to have gravity is going to equal that centripetal force. Okay, that's kind of the trick on that one. So you have everything you need to get the answer. Okay, so work through that worksheet and turn that in on class the next day. Okay, so hopefully this video helps out. I will upload it to YouTube and you'll have it in your Google Classroom to kind of look back at things for some example problems. Okay, thank you.